quantum mechanics and general relativity, what happens when they just clash so hard that the whole idea of reality being smooth and continuous just kind of, well, dissolves. That's exactly what we're diving into today. We're looking at the Planck length, this incredibly tiny scale, and what it means for space-time itself. Our mission, if you will, is to explore the really mind-bending stuff that happens when you take a particle's wave-like nature, its de Broglie wavelength, and squeeze it all the way down to the Planck length, a place where, frankly, our physics rulebook just doesn't seem to work anymore.
It really is a journey to the very edge of what we understand, maybe beyond. And to really get our heads around this, we'll need to navigate two pretty different domains of physics. You've got the quantum world, right? Particles, forces, the very small. And then there's the relativistic cosmos, gravity, space-time, the very large. And we'll be focusing on how these two, well, crucial lengths, scales, the dynamic de Broglie wavelength of a particle, and the static universal Planck length, how they don't just meet, but actually merge, fundamentally merge at this ultimate frontier.
It's kind of amazing when you think back to the early 20th century, how physics just got completely turned upside down, split into these two massive, powerful theories, quantum for the small stuff, relativity for the big picture, gravity and spacetime. And yeah, right at the heart of it are these two lengths, each telling us something different about reality.
You mentioned the de Broglie wavelength. That's about matter, right? It's dynamic, wave-like quantum side. And then the Planck length, totally different beast, not about matter itself, but a fundamental scale of space-time, the stage maybe, where the very fabric of space-time, the theory goes, might just dissolve, become quantum itself.
Exactly. And that convergence, where a particle's own quantum properties get so extreme, they're tied up with the quantum nature of space-time itself. That's precisely what leads us into this realm of quantum gravity. It's where our current physics kind of hits a wall, right?
Yeah.
And makes us ask, what does reality actually look like way down there? Okay, let's unpack the de Broglie wavelength first then, because that idea itself was revolutionary. Lou de Broglie, 1924. He just throws this out there. What if wave-particle duality isn't just for light? What if it's for everything? Every single particle, electrons, protons, you, me, planets, has a wave associated with it, a matter wave. I mean, the implication is staggering. Matter is waves, in a way. Your position isn't perfectly defined. And he gave us the equation lambda equals h over p wavelength linked to momentum.
And the physical meaning there is, well, it's critical. That wavelength tells you the scale where the particle's wave properties, things like interference, diffraction, actually become noticeable, observable. And this wasn't just theory. Davison and Germer, in 1927, they actually showed it. They diffracted electron beams off a nickel crystal. You can only explain that if electrons are acting like waves. It was huge, and later experiments confirmed it for neutrons, even whole atoms. So yeah, the Broglie waves are fundamental to quantum mechanics.
Right, so if everything has this wave nature, why aren't we seeing planets diffracting around stars, or my coffee cup diffracting through the doorway? Feels like we should see wavy stuff everywhere if it applies to everything.
Yeah, good question. It's not that the wave nature isn't there for your coffee cup. It absolutely is. But for everyday objects, macroscopic things, their momentum is just enormous compared to Planck's constant. So their de Broglie wavelength is incredibly, infinitesimally small, far too small to ever detect. So the wave nature is there, but it's completely hidden at our scale. It's a good reminder, actually, that quantum effects are universal, just not always obvious. And in the modern way of thinking about it, the de Broglie wave is seen as a probability wave. The amplitude of the wave tells you the probability of finding the particle right there, which means the particle isn't really at a point. It's smeared out, described by this wave function. Its existence is probabilistic.
Okay, that's the particle side. Now, shifting gears, the Planck length. You said it's about space-time itself, and it's not just some random tiny number someone picked. It comes from the bedrock constants of nature, right? Speed of light c, gravitational constant g, and Planck's constant h and par, the big three. And the number is just tiny beyond belief. 1.6 times 10 to the minus 35 meters. That's, 20 orders of magnitude smaller than a proton? And you said, here's where it gets really interesting.
It does, because its significance is, well, it's fundamental. The Planck length is generally believed to be the scale where our current physics just stops working. Both quantum mechanics and general relativity, their effects become equally strong, equally important down there. So you absolutely need a new theory, a unified theory of quantum gravity to make sense of it. Now, it's easy to think of it as like a pixel of space, the smallest possible distance. And some theories, like loop quantum gravity, do suggest something like that, a discrete structure. But more generally, it's seen as the scale where the whole idea of smooth, continuous spacetime breaks down. It becomes this sort of churning quantum foam. So think about what happens when a particle's de Broglie wavelength shrinks all the way down to the Planck length. It's more than just getting small. It's a profound shift. The de Broglie wavelength, remember, that's a dynamic property of the particle. The Planck length, that's a static property of the universe's laws, of space-time itself. When they meet, the particle isn't just moving through space-time anymore. Its quantum nature is so extreme it gets tangled up with the quantum nature of space-time. That's the doorway. That's quantum gravity.
Right, and to get a particle's wavelength down that small, it's not about making it tiny, paradoxically. It's about energy, insane amounts of energy. You mentioned it dissolves particle identity, like an electron becomes just energy. How does that work? There's something called the Planck momentum, which you get by setting the de Broglie wavelength equal to the Planck length.
Exactly. If you set lambda LP into Broglie's equation, lambda p is hp, you solve for the momentum, or p. That's the Planck momentum. And interestingly, it turns out to be a universal value. It doesn't depend on the particle you started with. It's about h bar divided by LP. And it connects directly to another fundamental quantity, the Planck mass. Now, at that kind of momentum, any particle, regardless of its rest mass, is going to be pushed incredibly close to the speed of light. Ultra-relativistic, we call it. In that situation, its energy is almost entirely kinetic. So E is approximately P times C. This leads straight to the Planck energy, EP, and the value is just colossal, around 1.22 times 10 to the 19 giga-electron volts.
10 to the 19 GeV. Okay, let's put that in perspective for you listening. The Large Hadron Collider, our biggest atom smasher, it runs at what, about 10,000 GeV, so 10 to the 4. And the most energetic particle ever detected hitting Earth from space, a cosmic ray, was maybe 3 times 10 to the 11 GeV. So the Planck energy is millions, billions of times higher than even that. It's just staggering. An energy scale we think only existed right at the very beginning of the universe, the Planck epoch.
That's the crucial point. To probe the Planck length requires reaching the Planck energy. They're intrinsically linked. If you could somehow give a particle that much energy, its de Broglie wavelength would shrink to the Planck length. And at that energy, the particle's own rest mass, what makes an electron, or a proton becomes almost irrelevant compared to the total energy involved.
Yeah.
The physics isn't about electrons or protons anymore. It's about the behavior of this immense concentration of pure energy. This idea of particle identity dissolving, the merging of forces and particles, that's exactly what physicists expect to see in a unified theory. It has to happen at this scale.
Wow. Okay, so the de Broglie wavelength hitting the Planck length implies Planck energy and dissolves particle identity. But you mentioned there's another way to see the importance of this scale, something about other lengths converging.
Yes, exactly. It's a really neat piece of theoretical convergence. It reinforces the idea that the Planck scale isn't just some mathematical curiosity. Think about any massive particle. It actually has 2 other fundamental length scales naturally associated with it, besides its de Broglie wavelength. One is quantum, the other is gravitational. First, there's the Compton wavelength, lambda, usually written as h bar over mc. This basically sets a limit on how precisely you can pin down a particle's location using quantum mechanics. If you try to probe it with photons energetic enough to measure distances smaller than its Compton wavelength, you actually risk creating new particle-antiparticle pairs out of the energy, which kind of defeats the purpose of locating the original particle, right? It's a fundamental quantum fuzziness limit. Second, there's the Schwarzschild radius, RS, which is 2gm over c squared. This is purely gravitational. It's the radius you'd have to compress a mass m into for it to collapse into a black hole, where its own gravity traps everything, even light.
Okay, so every particle has this quantum fuzziness scale, the Compton wavelength, and this potential black hole scale, the Schwarzschild radius. So is there a mass where these 2 scales become the same size? A point where the quantum fuzziness is the black hole radius?
That's the fascinating question. And yes, there is. If you just set the formula for the Compton wavelength, roughly h bar Bragg, equal to the formula for the Schwarzschild radius, 2gmc2, and solve for the mass m, you find that the mass required is almost exactly the Planck mass, mp, which is about the mass of a flea's egg, strangely enough. So 2.18 times 10 to 8 kilograms. And here's the kicker, as you said. If you take that Planck mass and plug it back into the formulas for the Compton wavelength and the Schwarzschild radius, they both come out to be the Planck length. Well, the Compton wavelength is exactly the Planck length, and the Schwarzschild radius is twice the Planck length, but they're the same order of magnitude.
That can't be a coincidence. So this Planck mass is special. What does this tell us? There's a correspondence.
Exactly. It's sometimes called the Compton-Schwarzschild correspondence, or maybe the black hole uncertainty principle. It gives us a kind of unified view. If a particle's mass is less than the Planck mass, its Compton wavelength, its quantum size, is larger than its Schwarzschild radius, its gravitational size. It behaves like a quantum particle. Quantum effects dominate. If its mass is greater than the Planck mass, its Schwarzschild radius is larger than its Compton wavelength. it behaves like a black hole. Gravity dominates. But at the Planck mass, the two descriptions merge. The Compton wavelength equals the Schwarzschild radius, roughly. This hypothetical object, a Planck particle, would be simultaneously a quantum particle at its localization limit and its own tiny black hole. Quantum mechanics and gravity become equally important. So pulling it all together, the de Broglie wavelength, the dynamic wave scale, the Compton wavelength, the quantum localization scale, and the Schwarzschild radius, the gravitational scale. They all point to the Planck length when you consider a particle possessing the Planck energy, which corresponds to the Planck mass. It's this beautiful triangulation, all converging on the same fundamental scale. It strongly suggests this isn't just math. It's telling us something deep about how quantum mechanics and gravity must unify.
Okay, so this convergence, this Planck scale, isn't just about unification. It also means our usual picture of space-time just breaks completely. Like you can't even measure anything smaller. It's an actual boundary.
That seems to be the implication, yes. Think about the standard Heisenberg uncertainty principle, the HUP. Delta x times delta p is greater than or equal to h bar over 2. In principle, that suggests you could measure position, delta x, as precisely as you want, if you're willing to accept infinite uncertainty in momentum, delta p, maybe by using a super high momentum probe. But that ignores gravity. A super high momentum probe is also super high energy, and Einstein tells us energy curves spacetime. So your high energy probe will drastically warp the very spacetime region you're trying to measure, messing up the measurement itself. When you try to account for this gravitational effect, you arrive at what's called the generalized uncertainty principle, or GUP. It adds an extra term to the HUP related to momentum squared. And the consequence is profound. It implies there's a minimum possible uncertainty in position. You can't measure position with infinite precision no matter what. And that minimum length and uncertainty, it turns out to be on the order of the Planck length. The GUP suggests it's physically impossible to resolve distances smaller than LP.
Wow, okay. But how? How is that minimum length enforced? What physically stops you from, say, building a microscope powerful enough?
The mechanism is thought to be gravity itself, specifically the formation of microscopic black holes. Let's do a thought experiment like physicists love to do. Say you want to measure something at the Planck length scale. You need a probe, maybe a photon, with a wavelength comparable to the Planck length, lambda around LP. But remember de Broglie. A wavelength of LP corresponds to the Planck momentum, which corresponds to the Planck energy, EP. Now, what happens if you try to concentrate that much energy, EP, which is equivalent to the Planck mass, MP, into a region the size of the Planck length, LP? You've just met the condition for creating a black hole. The Schwarzschild radius for the Planck mass is basically the Planck length, so your probe particle instantly collapses into a microscopic black hole. And the event horizon of that black hole acts like a curtain, hiding whatever information was inside. You can't see beyond it. If you try using an even more energetic probe, you just create a bigger black hole. You don't get better resolution. So gravity itself, through black hole formation, seems to enforce the Planck length as an operational boundary. You literally can't measure smaller.
That is wild. The act of measurement creates a black hole that prevents the measurement. And this ties into that idea of space-time foam you mentioned earlier, John Wheeler's idea.
Yes, exactly. Wheeler proposed back in 1955 that if you look at space-time on the Planck scale, it shouldn't be smooth at all. It should be subject to quantum fluctuations, just like everything else. The energy-time version of the uncertainty principle, delta E delta T equals h bar 2, implies that over incredibly short timescales like the Planck time, TP about 1043 seconds, huge fluctuations in energy, delta E, can occur spontaneously, even in empty space. These energy fluctuations could be large enough to briefly create virtual particle-antiparticle pairs, or even virtual black holes with about the Planck mass popping in and out of existence constantly. So instead of a smooth, placid stage, space-time at that level is this chaotic, churning, foamy texture. Wheeler called it quantum foam. You can see how these ideas connect, right? The GUP gives you a minimum length. Black hole formation provides the physical mechanism enforcing it, and space-time foam describes the underlying, inherently fluctuating nature of space-time itself at that scale. When you try to measure down there, you're not just disturbing a quiet vacuum, you're interacting with this pre-existing, seething chaos of virtual black holes and fluctuations. The breakdown of measurement is kind of inevitable.
So, given that our current physics just completely falls apart down there, we obviously need something new. A theory of quantum gravity. And the two big contenders, the main approaches people talk about, are string theory and loop quantum gravity. They sound very different, but you're saying they both end up pointing towards this Planck length limit.
That's one of the most compelling aspects, yes. They start from very different places, philosophically and mathematically. String theory, broadly speaking, says the fundamental building blocks aren't point particles, but tiny vibrating one-dimensional strings. And the characteristic size of these strings is thought to be around the Planck length. Different ways the string vibrates correspond to different particles, electrons, quarks, photons. Crucially, also the graviton, the particle that carries gravity. So gravity emerges naturally from the theory, and because strings are extended, not points, they sort of smear out interactions, which helps get rid of problematic infinities that plague point-particle theories. String theory also has features like T-duality, which inherently suggest a minimum length scale trying to probe smaller distances, effectively wraps the string around a compact dimension and makes it loop bigger. Loop quantum gravity, or LQG, takes a, radically different approach. It doesn't start with strings or particles on a background spacetime. It tries to apply the principles of quantum mechanics directly to spacetime itself, to quantize geometry. And when you do that, LQG predicts that space isn't continuous. It has a discrete, granular structure at the Planck scale. Space is built up from fundamental quantum excitations of the gravitational field, forming structures called spin networks, or spin foams. A key prediction is that quantities like area and volume are quantized. They come in discrete packets, with the smallest possible area being related to the Planck length squared and the smallest volume related to the Planck length cubed. So in LQG, the Planck length really is like the fundamental pixel size of space. And notably, it does this within the familiar 3 space plus 1 time dimensions, without needing extra dimensions like string theory typically does.
Okay, so let me see if I have the core difference right. String theory starts by quantizing the things in space-time, the particles, as strings, and finds that this implies a minimum length for space-time itself, often needing extra dimensions. Whereas loop quantum gravity starts by quantizing space-time itself, the stage, and finds it's made of minimal chunks related to the Planck length in our normal dimensions. Is that a fair summary?
That's a very good way to put it, yeah. Quantizing the actors versus quantizing the stage. 2 fundamentally different starting points. And yet, despite these huge differences in approach and assumptions, both frameworks independently arrive at the conclusion that the Planck length represents some kind of fundamental limit, either as the inherent size of the fundamental constituents or as the quantum resolution limit of spacetime geometry itself. This convergence coming from such different directions is really quite remarkable. It provides strong, albeit circumstantial evidence that this idea of a minimal length or a breakdown of smooth spacetime at the Planck scale is likely a real feature of quantum gravity, whatever the final theory turns out to be.
So recapping this whole journey then, we started asking what happens when a particle's wave nature, its Broglie wavelength, gets squeezed down to the Planck length. We found it requires this unimaginable Planck energy, an energy so high it basically dissolves the particle's identity into pure energy. Then we saw this amazing convergence, the particle's wave scale, Broglie, its quantum fuzziness scale, Compton, and its gravitational collapse scale, Schwarzschild, all meet at the Planck length, precisely when the particle has the Planck energy. At that point, the particle literally becomes its own microscopic black hole. It's where quantum mechanics and gravity absolutely have to merge.
Exactly, and this merger isn't gentle. It implies that our variability to measure space and time breaks down, as described by the generalized uncertainty principle. Gravity itself enforces this limit through black hole formation. You simply can't see smaller. And underlying all this is the idea that spacetime isn't a smooth, passive background, but a dynamic, fluctuating quantum foam at the Planck scale. The particle and the stage merge into one inseparable quantum system.
It's an incredible picture, theoretically. But the huge challenge, obviously, is figuring out which theory, if any, is right. Or maybe it's something completely different. String theory, loop quantum gravity, they have these deep mathematical and philosophical differences, and resolving them is tough. And it's made tougher by what you called the experimental desert, right? The Planck energy is just so far beyond anything we can create in a lab. Direct tests seem almost impossible right now. It makes you wonder how we'll ever know.
It's a massive challenge, no doubt. But physicists are creative. We can't build a Planck energy collider, but we can look for subtle, indirect clues. One way is cosmology, looking very carefully at the cosmic microwave background radiation, the leftover heat from the Big Bang, and also the way galaxies are clustered across the universe. The idea is that tiny quantum gravitational effects from the Planck epoch, right after the Big Bang, might have left faint imprints that got stretched out as the universe expanded, potentially visible today. Another approach is looking at light from extremely distant events, like gamma-ray bursts. Some models of quantum foam predict that high-energy photons might travel slightly slower or faster than low-energy ones through this foamy spacetime. So far, observations haven't seen this effect, which puts tight constraints on those specific models, but the search continues. And closer to home, there's a push for ultra-high precision lab experiments. using things like incredibly accurate atomic clocks or sensitive matter wave interferometers to test for tiny deviations from known physics, like violations of Lorentz invariance, the principle that the laws of physics are the same for all observers, which some quantum gravity theories predict might happen at levels we could potentially detect.
So the convergence of the de Broglie wavelength with the Planck length, it really does mark this absolute boundary of where our current physics works. It seems to be the point where everything we thought was separate space, time, matter, energy has to merge into some new, unified, and still deeply mysterious reality. Figuring out the laws that govern that ultimate scale, well, it really feels like the central, most profound challenge for physics in the 21st century, doesn't it?